Okay, welcome back everyone. So as a second speaker today, we are delighted to have Domenico Orlando from Torino, who is going to tell us about capital model and large charge.
Okay. So first of all, thank you very much for coming. And I would like to canonically thank the organizers for giving me the opportunity to present my work. But for once, I really mean it. So I do actually mean it because I'm really honestly delighted to be in Paris again. And okay, actually, EHB is the first place where I've given a real talk. It was upstairs, and I shall not say how many years ago that was. And another thing is that the things I'm going to talk about all started with a paper that we wrote 6 years ago now, 100 meters down the way, because I was at the Economic Model at the time. Okay, so today I'm going to do a very, well, I try not to be too specific, but I try to give a little bit of a flavor of this kind of work that we've been doing with my collaborators in the last years, and has led to a number of papers that are here in the first slide. Should you be interested in learning about it, what I could advise is to look at this one here in bold, because this one here is some sort of quick review that we wrote last year to try to make a little bit the point on what we have learned so far. But as you see, we kept working. So, I mean, there's not 5 or 6 papers that have appeared since. Anyway, before I actually start with my talk, I'd like to present you my collaborators. And as you see, we pretty much delocalized because we have people that go from the US to Japan, and pretty much in geographical order. On the east, there's Simon Henderman at the University of Tokyo. Then there's Debashish Banerjee, who's in Kolkata, Masataka Watanabe, who's now at Weizmann, Francesco Zannino, who is in some superposition between Denmark and Italy. Then there's Susanne Redford and a group in Bern. And then there is Luis Alvarez Gomez, who's Simon Center, and Shailesh Chandrasekaran, who's at Duke. So some of these people you surely know, some you don't. One of the reasons why you shouldn't, well, I don't expect you to know some of these people, is that there are 2 of them, who are Debashish and Shailesh. These are lattice field people, well, the lattice people, so they do things which are slightly different from what we usually do. And actually, I'm super happy to say that for once we managed to get close enough to real physics that we could go to lattice people and tell them, try to do this, we should see that. Okay. So, okay, what I will be talking about today is mainly, apart from what's going to happen at the end, conformative theories. So typically here, there is a slide where I try to convince you that it's important and we should all be studying conformative theories, but you know why. So I think I skipped that. On the other hand, what I would like to stress about conformative theories is that generically, they are hard. So why are they generically hard? Well, because CFT is a conformer, right? So they come with upper scale. It's what you usually find at the end of an energy flow, or at the beginning anyway. And so this means that typically, at least if your thing is natural, whatever natural means exactly, it's going to be hard to do. It's going to be hard to study because usually you'd like to have more parameters to play with your physics, right? Now, our idea is very simple, actually. Is maybe if you have a CFT that has, on top of its nice conformal structure, also some global symmetry, but you make use, you might be lucky and be able to make use of it to find some special pieces of the theory where there is some sort of simplifying limit where you can actually do computations. Okay, so that's the idea. So if you want to really keep one message from this talk, is that our idea is very simple. So you have your CFT or your quantum field theory. Yeah? This works more generally than just CFTs. And you have a global charge, you have global symmetry. You can divide your Hilbert space into sectors of fixed charge. You can make it more or less precise, this statement. And then, if you're lucky, it might be that sector by sector, you can be able to write an effective theory that describes the physics of that set. So again, the theories will be strongly coupled, okay? I will never pretend I'll be able to solve the theory unless I have something else to do it. But sector by sector, maybe, if I'm lucky enough, it's going to be possible to write some sort of effective theory. Okay, so good, blah, blah, blah. That's all very cute, but so concretely, what can I do? So today, as I said, I will concentrate, well, as the title says, I concentrate on vector model. And the reason is that it's the easiest case where we can work, or we can make all of the machinery work. And in particular, I consider something that we always start with when we try to learn about conformity theories, which is the ON vector model. Okay, so I have n bosons, and they transform into vector. And we know from the work of Wilson and Fisher that if we apply to the fourth, this thing will fly in the infrared, will flow in the infrared to some non-trivial field theory, this conformity theory, the Western Fisher fixed. Obviously, in the last 50 years, more or less since this was studied, people have calculated everything possible, right? Now, the problem is that even so, there were things that, I mean, it was not obvious how to extract. So in particular, take the example of the O2 model, right? So in the case of the O2 model, clearly you cannot do large n, because 2 is really not large, right? And if you want to do it really in 3 dimensions, you cannot do 4 minus epsilon, because 1 is not small. Of course, you can do bootstrap, but with bootstrap, you can get, it gets very complicated at some point, at least at the point where in the part of the theory we're interested in, it seems to get very complicated. Okay, so what we are saying is that actually, if you know, it's an ON vector model, so it has an ON global symmetry, so there is a definition of charge. So take, for example, O2. There's a sense in which your operators are charged. You can ask a simple question. Can I compute the conformal dimension for given charge of the operator that has the lowest dimension? It turns out that the answer is yes. And there is a very, 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 very simple formula that tells you this dimension. And it's this formula here. So if you compute the conformal dimension of the lowest operator of charge Q, you're going to find an expansion that starts with Q to the 3/2 with some coefficient, Q to the 1/2, some coefficient, a number, which I can actually give you with any precision you want, but here just written the first 4 digits. And then whatever happens afterwards is going to be controlled by inverse powers of the charge. You will see very soon why in our construction, unless we can do something else, these 2 numbers remain unknown. So essentially, these are ingredients that we need to put in for our machinery. This said, this is a very, very simple formula that, you know, someone might have computed in the 70s. There's literally no reason why they didn't. So you find this thing, and this was in the first paper already, and you wonder, so is it true? You go to check in and see, no, there's not this formula. Okay. Oh. How do you know if it's true? But the only way is to compute the same things differently. And then you hope that it works. But as I said, it's complicated. The CO2 model in 3 dimensions. It's actually complicated. I mean, the question is well posed, but it's not obvious how to actually compute this thing. So what we did instead is that we went to lattice people. You know, it's the CO2 model. They should be able to put it on a lattice and answer this question. Out. It's a relatively difficult question even on the lattice, especially when Q becomes large. For technical reason, but the reason is very simple. It's very difficult to put a lot of charge in one point, even on a lattice. Nonetheless, I was very lucky because I met these people, Shailesh and Debashish, which are incredibly good. So after we spent a couple of months trying to understand each other, they spent a year doing calculations, and that's what they gave us. So this is real, huh? So this is what we're real. It's as real as it gets in the sense that that's what comes out of the lattice. This is a conformal dimension for the lowest operator, charge Q, in the O2 model. Now, at this point, the usual question is, I don't believe you. Where are the error bars? I told you my friends are really good. Huh? The error bars are less than a pixel. So. And the line that you see joining so strangely nicely all these points is exactly what I said before. This is q to the 3/2 plus q to the 1/2 plus 0.094. And remember, there were two coefficients I didn't know in my formula. Feel free to fit them on any of these 2 points. So if anything, even though there were things I didn't know, this was a prediction. You give me 2 points, I give you 11. Now, of course, you see this thing here, and you're like, wow. So something we're doing right for sure, but it looks like there's a lot you need to understand. Because remember, the formula I told you before was supposed to work when Q is large. Now, let's go back here later, okay?
In that picture of Q is large, you mean apparently it's just above 0. That's what you're telling us.
Let me get it. I shall say the word resurgence more than once. Okay? So, okay, how do we do that? So before we get to the details,
So did you just say this chip is set to what? Because there was also this order 1/square root of Q terms, or are you just setting that to 0 or
3 terms.
just the first 3? Okay.
That's right. Again, researchers will tell me why this is a good idea, but I have to get in there. Okay. For the moment, I don't know. For the moment, I'm completely ignorant. So for the moment, I have my effective theory that I explained. The moment I construct, I keep the first 2 terms and let's see what happens. That's really an experimental approach. Okay. So how do we construct this effective theory? You know, when you learn about normalization, they tell you what Wilson tells you. You take your high energy degrees of freedom, your low energy degrees of freedom, you integrate out the high energy degrees of freedom, what remains is effective action, and that's what you need to do. And yes, and typically, if you teach that, you see that your students will. And in fact, you feel bad because this is false, right? This is a great lie. You wish you could do that. What you said is not what you do, it's what you would do if you could. So how do you actually write effective field theories? Well, you have to understand the physics. Okay. So we're actually in the same type of problem that people have when they start writing the physics of violence. They didn't know what was the real theory. In this case, we don't know in a sense because we are fixed point, it's strongly coupled, we don't know what there is. So we need to figure out how the physics works. And then you need to understand what are the scales in the problem. But it's a CFT. Where do the scales come from? One scale is sort of easy because you can say, oh, I can put my system in the box. Well, yes, no. Can you really put a CFT in a box? But that's a bit of a tricky question. What does exactly mean a box for a CFT? Since you have line invariants, it's less trivial than it sounds. But okay, for the moment, let me put it in a box. And then, if I have a global charge, I can decide to fix the charge density or the charge. Once it's in the box, it's the same thing. So all of a sudden, even though my theory had no scales, it's a CFT, I have 2 scales in my problem. One is the size of the box, one is the charge density. That's also dimension 4. They're different. I can try to write an effective action which has a cutoff, which is in between. Okay. But you see, this is literally what you do for piles, for example. You have a low energy scale, here it's fixed by the size of the box. You have a high energy scale, here it's fixed by the charge density. If you manage to write an effective action in between, automatically, by construction, your effective action will be perturbative and controlled by the ratio of the high energy scale and the low energy scale. That's always true, okay? Like Zumino 1970, or, well, I'm sure we have in the audience people that know that this thing is even before, probably. So, what I'm trying to say is that if I manage to write such a thing, then automatically this thing will be a perturbative theory And the perturbation parameter in this perturbative theory will be the ratio of these two scales, which ends up being 1/q. So as long as Q is large, I have what is technically called scale separation. And I should be able to write an effective. So that's really the idea that we have behind. So, okay, let me go back a little bit here and how Marius observed. Of course, I said I keep saying large, I say scale separation, and then I do this, and it turns out that this thing seems to be working not when Q is 100, but when Q is 2 or even 1. So, is it strange? Is it really, really strange? So should I be worried, or is it sort of something I could have hoped for? Well, you see, this is not the first time that this work happens. The gentleman in the picture is to the edge. Okay. So, you know, there is a thing called Regge trajectories. And they work the same. If you really look at Regge theory, this stuff should only work when the spin is very large. But experimentally, this is real result of real experiment. This is not just a drawing, that's real physics. It turns out that the lines go down all the way till, even though the speed, it shouldn't be working, but it does work. So somehow, I would say that more generically, there's something that we still need to understand well enough, is some sort of unreasonable effectiveness of these effective field theories, okay? So that's what's happening. And if it happens for any trajectories, it happens here. Good. So, of course, a lot of work has been done. For example, Shota has contributed a lot, very nice things, very lately in this kind of business. Of course, there's no way I have any time to tell you everything about or anything about all this work here. So I will not put any references during the talk. All the references are here. So if you're actually interested in what kind of things you can do, I'll be concentrating on this and large N, but you can do a lot of other things. Holography, again, Shota did things about holography, which is extremely interesting. You can look at things in double scalings. You can see what happens in case you have conformal field theories which are non-relativistic. You can ask what happens when you have supersymmetry. You can ask, can I understand these things via bootstrap? Yes. The answer is yes. There's a lot of work, but that's not what I'm going to do today because I just want to give you the ideas. Okay. So concretely, this was an introduction. So what am I really going to do? Okay, this was not a nice pictures. First of all, I show you how to construct the effective field theory for the O2 model. The thing that does give you that curve that then reproduces indeed what you find on lattice. After that, I try to show you that actually all that I'm saying is not unreasonable. So how can I do that? Well, the best way to do that is to take a system where I can actually do calculations. You see, the O2 model is strongly coupled. It's very complicated. You don't even know how to, if there is an action, you don't know what to do. But since you're working in vector models, one thing you can do is just say, okay, instead of O2, I look at ON, and then I set them to be very large. In that case, I have control. I can do the calculations. So what I will do is that I take the ON model, send them to infinity, compute the same things, and see what comes out. Now, once you have ON, though, you actually have a lot more power than you had before. In particular, you don't care if the charge is large or the charge is small. You use large N. Okay. So it will turn out that I can put a bit on more solid foundations, so more solid mathematical foundations, this asymptotic expansion that I'm writing. So I will answer Miguel's question. So why did you keep 3 terms? Why didn't you keep 5 or 2 or what did you throw away? Okay, and why? Do you expect it to work? And to answer these questions, I will need resurgence. And resurgence, honestly, I only know how to use in this kind of business when I have another controlling parameter, in this case, the large N. Finally, depending on time, I show you how you can use, if you want, you can also think of large charge for fixing the charge as a trick. So in particular, it's something that we've been doing lately. You can go away from the fixed point, and then try to see if fixing the charge is actually useful for something else. In particular, this something else is that you can compute exactly an effective potential for the UN model, a large N door. You compute it without doing a single Feynman diagram. Okay, just get it. Resounds, already done, ready for study. In particular, since you don't have an asymptotic, you don't have an expansion of the effective potential, but you just have to think, you can ask questions related to the convexity of the effective potential. The convexity, well, the thing here, I'm a bit ashamed of saying these things, but it's convex. It has to be convex. If you compute it and it's not convex, then you have to understand what you'll be doing. So in particular, what I will be showing you is that you can repeat all this game in 3, 4, 5, 27 dimensions, at least formally works. What I will show you is that if you try to work on the vector model in dimension higher than 4, there's a very simple way of showing that there's something is going wrong, which is that you compute the effective potential and you find that it's not convex. Or alternatively, you can say you will see that the theory, since I'll be able to write the effective potential along the flow, I show you that it's a theory that needs a UV completion. And in particular, there is a natural UV completion, but it's in terms of a complex field theory. And the nice thing is that in this way, I will reproduce, again, I will not be writing a single Feynman diagram. I will reproduce a bunch of results that are known about, for example, the vector model in 5 dimensions, which I find were complicated to see. And here this will sort of come out naturally, just because we know the effective potential. Okay, this concludes my introductory part without formula. If you have questions, it's a good moment. Otherwise, I go on. But from now on, I shall be explicit. I'll put formulas, and okay, I'll try to be less verbose. Anything? Yes.
Sorry.
Okay. It's up to the two of you.
Go ahead. Okay. So you were doing their own model in 2+1 dimensions,
right.
And then you mentioned this complex CFT in D bigger than 4 and less than 6.
That's right. Well, think of it, and if you want, let me be Euclidean. So I'll be doing in 3 dimensions, and then in 4, 5, 6, and higher dimension. Okay. But that's what I will do. But hopefully I get that because it's pretty much at the end. Rebecca?
What is effectivity theory? What you can do with it? I mean, you cannot compute correlators. Right?
Yes.
You can.
I can compute, well, it's a CFT. No? So from this effectivity theory, I can compute conformal dimensions and 3-point functions. So at least in the limit in which the effectivity theory works, I have all the CFT data.
But if I have, even if I just put a scale, then I have a separation. One function that is a separation, so it's a function of the separation of the scale.
No, you see, okay, let me do it, and then maybe it will be more clear what I'm doing. Okay, so in particular, since I've been using the state operator correspondence, the structure of 2-point function, and it's automatically right, if that's what works. Let me do it a little bit, and then you say you'll be clear. Okay, so let's construct this theory for O2, and again, we just want to use the symmetry of this thing. So what's the idea? Again, the O2 model is just the non-trivial fixed points that you get if you take phi to the 4th and see what happens in the invertex. Okay, so I'll be very cavalier between saying 1 + 2 dimensions and 3 dimensions, but that's what I mean. No, this thing is strongly coupled, and it's a real thing, right? So this is really the Superfruit transition of the helium 4. It's something you can see in the laboratory. People even brought on space shuttle to see what happens in space. And usually you study it because you want to understand spontaneous symmetry breaking, but concretely, in perturbation theory, you cannot do nothing because in 4-7 dimensions, you cannot really do it. Well, you can sort of do it, it sort of works, but it's not clear how. And also a large n, you cannot really trust what you get because n is 2. So typically, either you put it on the lattice or you bootstrap it and see what you can extract out of it. Okay. Now, so what I want to do, as I said again and again, is to consider a subsector of its charge, Q. So what happens if I'm just concentrating on a subsector of the theory? If I'm just looking at a subsector of the theory, the state of minimal energy in that subsector has a charge. So it breaks the symmetry. Easy peasy. But this thing will look like a spontaneous symmetry breaking from the point of view of the theory, because it's a state that breaks the symmetry. Which means that there's a non-perturbative statement, which is there's a Goldstone boson. So my claim is, if I consider a sector of fixed charge, the physics must be described at low energy by a Goldstone boson. Let me write a Goldstone boson. So how do you write a Goldstone boson? Well, you want to write your action, and naturally you start with two derivatives. What is easier than that? Maybe you even have a cosmological term. I told you that I want to put this thing in a box. Maybe this thing is going to be useful, right? So that's the first thing you write. And you're, of course, completely wrong. The reason why you're wrong is that your Goldstone boson essentially, well, you can make it complicated and say this is the algebra, but the point is the Goldstone boson is dimensionless. You want to write an action in 3 dimensions, you must write something that has dimension 3. You need dimensional objects. For example, this F pi that I've written here, because I have ions in mind, and this cosmological constant term, this CQ, right? Well, so this must be wrong. Why must this be wrong? Because it's true that the physics is Goldstone boson, but it's also true that it's a CFT. These are no dimensional full parameters. I cannot write, this can never be a good description for a CFT anywhere, because they are states. So what do you do? Well, the solution is classically known. It's like you just look at Coleman's lectures on 1970. You are the dilettante. You can dress up whatever term you have in your action, adding a dilettante, which is just a field that transforms non-linearly under Bayes scaling. And there is a recipe, essentially, that tells you how to dress up everything. So instead of adding chi, you have to dress up, for example, a kinetic term with e to the minus 2 f sigma. F is dimensionful again. And then if you have the operator here that has dimension 0, you have to dress it up like this. And then if you want to make even if you want to make things even slightly more complicated, you're even free to add a kinetic term for this field. After all, you put it in. Okay? And also this, you dress up exactly the same way. If you dress it, and you use the fact that the dilettante transforms non-linearly under Bayes scaling, you get something which is at least composed of scaling variant. Okay? Actually, slightly variant. Now, if you think of it like that, then this starts to make a little bit more sense, because what's really happening here is that you fix the charge. Fixing the charge is a condition that breaks Lorentz invariance. Remember, the charge is the 0th component of the current. You fix in that, you break Lorentz invariance. So not only if I break Lorentz invariance, necessarily I've also broken Copolar invariance. So I don't just have a Goldstone coming from breaking U1 symmetry. I also have a Goldstone coming from the Copolar symmetry. These are the two Goldstones. Now, you look at this action and you think, my God, that's horrible. This is why looks are very deceiving, you know? You take these two Goldstones and you put them together to make complex fields. Literally sigma plus f pi chi. Okay? And then you exponentiate that. And then you just change variables. Instead of writing your action in terms of sigma and chi, you're writing in terms of this phi, which is just the exponential. Ta-da! Your action simplifies radically. It's just phi to the 6. All your dimensional full objects that you put in the theory, remember there was phi, there was the c, there was another f that was coming with the dilettante. Well, only combination that are dimensionless of these survive in this action. It has to be, because we're in 3 dimensions, canonical dimension of the field is 1/2. This has to have dimension 3 at the end of the day, and that's 5 to the 6. And the couplings that appear in that action are dimensionless. Now, don't be fooled. This phi that I write here and the phi that we had in phi to the 4th and then close to the weight sufficient point, these are completely different objects. They have nothing to do with each other. Well, they do have a lot to do with each other, but you don't know how. You say, you have fields in the ultraviolet, then you have to try to follow them all the way down the slope, and at the end, I'm claiming that that's an effective description that it captures the infrared. Now, of course, you should be scared, because this is not supposed to work. It's not supposed, I mean, for one, when I say phi of a canonical dimension 1/2, and then I write phi to 6, you can tell me immediately that, so what? The quantum corrections will kill this thing before you even start. So what I have to convince you is that that's not true. That at least if you are in the right limit, then the quantum corrections are so small that that's a good approximation of it. Okay, so what's happening? You see, there's a bit of a problem because this is phi to the 6, and I even want to quantize it, and you're not supposed to be able to quantize phi to the 6. It's not quadratic. Well, the story is a bit more complicated because, again, I keep saying I fix the charge. When you fix the charge, what happens is that effectively you are adding to your potential a centrifugal term. Think of how you get the charge, right? So you have the chi dot square over a square chi dot square. That's the charge essentially, charge squared divided by r squared. So effectively, what's happening? Well, it's true that my system is phi to the 6, but it's also true that when I fix the charge in the sector of fixed charge, your effective potential will look more like this. This is 1 over a squared. That's as I said, that's a centrifugal term. Which means that the real vacuum of the theory is not in 0, where I have no idea what happens. The real vacuum of the theory at fixed charge is somewhere here in between. This somewhere depends on the charge that I fixed. And around that, it goes quadratic. You can do perturbation here. And that's the whole point. Once your effective potential is here and the curvature of this thing depends on the charge, it means that the quantum corrections that ultimately depend on how this thing is curved around there are controlled by the charge. That's the idea. Okay. So you can do it explicitly. You can look for a solution at fixed charge. What you find is that the solution looks like this. The sigma field dilaton is constant. And the chi field, the Gaussian of the U1 symmetry that you've broken, has to become linear in time. I broke Lorentz invariance. That's normal, it's a charge. Then you compute it as functions of the charge, and you find that this mu here that appears has to go like charge to 1/2. So when the charge is large, mu is large. And similarly, the expectation value of the dilaton, well, here it looks small, and in truth it's large because it's log of that, so it's just minus that. Okay. So here it is. You take the classical solution to your action, and you find the energy is some coefficient. And this coefficient, where does it come from? Well, this comes from the coefficients you have to put at the beginning, and you have no idea about. The things that were dimension full and then became dimensionless. Well, no matter that, I know nothing about this. So this coefficient here will depend on that. The coefficient here will depend on that. But the structure, charge to the 3/2, charge to the 1/2, the effect of geometry. Here there's a volume, here's a curvature of the space in which I'm doing all this game. This is fixed. Now, why would you care about energies? Well, oh, sorry, I skipped the slide. Okay, so that's just the gamma state, right? Now, you want to quantize this thing. How do you quantize it? Let's just try calculations and see what happens. Well, what you find is that you have two modes. One mode is massless. And since you broke Lorentz invariance, a priori you don't know what massless means here. It just means that when p goes to 0, omega is 0, but that's it. So what you find is that it has a very characteristic way of behaving, where omega is 1 over square root of 2p. So it's not 1. The speed of light is 1 of square root of 2. And it turns out that this you should have expected from the beginning. Because you see, that's the CFT, right? So the energy momentum tensor has to be traced. Here we've given up on Lorentz invariance. So there is another way of making something traceless. Is if the energy part in the T00 and the rest cancel each other. Okay? But if there's one energy and two momentum dimensions, so if there is a 1/2 relative, this can make 0. Here it is. This object is scaling invariant. Just scaling invariant in a strange way, because we gave up on Lorentz invariance. But still has T mu equal to 0. In D dimension, this would have been a D. What about the other mode? There were two modes. Well, the other mode is massive, and that's the cool thing. It's massive with a mass that goes like mu, which I remind you goes like Q, so it has a big mass. So what's the physics? The physics is ground state, massless oscillations, everything else, every single Feynman diagram you will write will have one of these modes flowing in. But these are massive, with mass proportional to charge to the 1/2. Any quantum correction will keep getting all these 1 over Q's inside, just because there is the massive thing flowing inside. You see it? I don't even need to compute them. I know it already. Very good. So, of course, once you have a massive object, you can just say, why don't I integrate it out? After all, a low energy will not contribute. And in fact, you can do it. But you have to be careful. Because, first of all, technically it's complicated. So, in truth, what you do, you try to write an action that only contains the massless stuff, only the massless type. Now we know there is one. It has to have dimension 3. You can write this, the mu chi to the 3/2. And then you have a curvature, which has dimension 2. So to make 3, you can have the mu chi to the 1/2. Now, this seems completely crazy as an action. But it's okay, it's fine. Don't be afraid. This has to be expanded around the vacuum that we found before. The vacuum we found before was mu t. This is not around 0. Even if there is funny powers, who cares? You can expand it around that. It's not just be quadratic. You can quantize this thing. You cannot quantize it around 0. You cannot quantize it at 0 charge. But you can quantize it at fixed charge. And if the charge is large enough, all the quantum corrections, as we've seen before, will be controlled precisely the 1 over 2. It's very easy. So why am I insisting about energies and blah, 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 blah? Well, because, again, I want to go, this is a CFT. So it means that sector by sector, everywhere, there has to be a state operator correspondence. I'm interested in computing conformal dimensions. I can think of them as energies on the cylinder. You know, you can always map R to D to R cross S D minus 1. And that's where we are. We are on the cylinder. When I say I put my system in a box, what I really mean is that I put it on a sphere. Because in my mind, what I'm really doing is a cylinder, which I know is conformally flat. So this thing of, I said before at the beginning, oh, I'm putting my theory in a box. Well, I am and then I'm not. As in, I'm studying the theory of the sphere, on the cylinder really, so that I compute energies and this giving conformal dimensions. But at the same time, what I'm really computing is the conformal dimensions of flat space. So you have to be careful. That's all I'm trying to say. By invariance, if you are in the box or not, it's a matter of frames for many things. Okay. So at this point, the last thing that remains for me to do is see what are the quantum corrections on top of the energy that I found before. Because it will be just the quantum corrections on top of the conformal dimensions. Well, the leading contribution to the quantum corrections comes from the Casimir energy of Goldstone. Not just a massless. You can compute it in 2 billion ways. But you put yourself on a sphere on S2, so that the energy you get is directly conformal dimension. Now, this term is Q independent, because I Q to the 0. And then you can prove, I cannot do it for you now, but you can prove that that's the only possible term that appears in the theory that goes like Q, that scales like Q to the 0. Roughly, the idea is every time I have any other term, we'll have the other massive object running around, and so it's going to get masses of that thing that go like the charge. So this means that A, this term Q3 and Q1 that we found from the ground states are the only ones. There are no quantum corrections to this. It doesn't matter. These are Wilsonian coefficients in front. I still don't know them. But there are no corrections to those anyway. On top of that, the only term that I can write that has Q to the 0 scaling is this Casimir energy, which I can't compute. There is no counter term in my theory in 3 dimensions that can change this thing. This is true. There's no freedom here. In 4 dimensions, it's different. There are anomalies, but there are no anomalies here. We're okay. So I can compute this number. And this is a prediction of the theory. The claim is that any ON model will work exactly like that. I've done it for O2 in a video, sorry for ON. The coefficients here, the Wilsonian coefficients here will change. The 0094 is a universal prediction. Okay, so let me go back a little bit just to make the point of what we're missing. So we started from a CFT, so it's something where there's no mass gap, there's no particles really, there's no Lagrangian. We picked a sector, and in this sector, turns out that the physics is described by a very simple semi-classical configuration, plus these Wolfson fluctuations. Okay. And even though the full theory has no small parameters, we can write a very simple effective field theory as long as we just restrain ourselves to one sector where the charge is large enough. And in this sector, we can actually use perturbation theory. That's it. Now, you can go and decide this was the vector model, the O2 vector model, you can try to do N, you can try to think of something else, you can think, does CPN work like that? Does your favorite system, does it work like that? There is no, you cannot know, at least we don't know what are the conditions under which this works. Okay? So we are coming up with the impression that that's a generic behavior of CFT, but I have no proof. In particular, a supersymmetric conformal theory will work a little bit differently. And if you're interested, just ask me questions, because I don't have the time to do it now. What I will do, on the other hand, is try to repeat this calculation now for a theory where I can control charge, large, and N, which is also large. Why? Because in this limit here, I can actually compute stuff independently. I will compute the same quantities and try to see if I get the same, or I don't get the same. Okay. So before I move to that, other questions? Okay. Very good. So let's do it. Let's actually solve this problem for the OM model. So what I want to compute once more are the conformal dimensions for the operators, lowest operator of a given charge in the ON model in the limit of large n. How do I do that? Well, I write the ON model. And then what I want to really write is a partition function of fixed charge. Okay, so it's canonical partition function. To do it together with the usual e to the minus beta h in the trace, I put a bunch of deltas that fix the charge. You know, you have the ON model, O2n, let's say O2n to make it a bit simpler, just for notation. So you have all this, you can think of the carton, this thing as rotating the fields in pairs. So you have a bunch of U1s, you fix them. And the way to fix them is that you put the delta, where Q hat is the operator, it's the natural operator that rotates these things in as complex fields, and Q and I are a bunch of numbers. So you're going to get something of fixed charge. Okay? And then using the same logic as before, you do this computation of the two-sphere, and the log of the partition function is the free energy, and if you leave it on the two-sphere, what you get is automatically conformal dimension, because state operator corresponds. Okay.
So what's the, sorry,
Yes.
what do you mean by charge here? It's one, it's the sum of several charges.
Oh, okay, very good. Thank you. Okay, so that's a mess. It's a mess before you think a bit of the representation theory, and I did really not want to enter into that. So I'm doing it. You have O2n. The things you can fix are all the cartons. Okay. Now, this you can fix independently because these are separate, well, they commute, they carton. So you can write something where you fix each one of them. Now, in truth, the story is a bit more complicated because this is not a When invariant statement. I can always do a When rotation which mixes this thing, even though I thought I was fixing the carton. But now I can act with When, and this screws up everything. So the real thing I should be doing is not a story of fixed charge, but a story of fixed representation. That's a real statement. You see, in U1, the charge identifies the representation. It's a million. Non-U1, well, it's really the representation that I should be fixing. Now, I don't want to spend the next half hour trying to explain how it works. So I do the following. I choose the simplest case possible, which is choosing the completely symmetric representation. So just a line of boxes, which is very long. So that's what is large. My charge will be the number of boxes. And it turns out that this is completely equivalent to fixing only one of the charges and leaving all the others free. If you do that, you will end up automatically in completely symmetric representation, and Q is the number of boxes. So that's the answer. Why is it so? I will not tell you. Very good. So now let's do the calculation. So we do the calculation. We rewrite my delta functions in terms of integrals. So in here it remains the operator, and now it looks like a Fourier transform. So it looks like a Fourier transform for something where inside the action, well, inside the Hamiltonian really, there's this charge operator. So this is now a grand canonical system because it's like I'm putting a theta, I theta really, is the chemical potential for the charge element. And then I'm doing the Fourier transform of that, which fixes the charge instead. So this is what you do in thermodynamics as well, but you usually don't think of it. Because in thermodynamics, you don't really write a Fourier transform, but you write a Legendre transform. Turns out that that Legendre transform is just the limit of this thing here. The thermodynamical limit of this thing here is usual thermodynamics. So now you need to write this action here. You want to write as a path integral. Turns out that the best way of doing it is just to take this chemical potential here and put it in the action as a flat connection. It's the same thing. Because if you see it from here, it's like changing the boundary condition once you go around in time. But changing the boundary conditions once you go around in time is the same thing as putting a flat connection in time direction. The long and the short is that you get that action there. Okay? Well, now it looks like the same as before, but it isn't because there's a covariant derivative. And the covariant derivative only has a flat connection in the zero direction, which depends on theta, which is the thing on which we integrate. But that's okay, because from now on, you just take the sum and you just follow the book. Okay? So from here on, you know what to do, because you do your Stratton-Aldrich transformation. So instead of 5 to the 4th, you introduce an extra field, lambda. So you get a cubic action, but all the fields phi appear quadratically, so you can integrate them out. So just a Gaussian integral for the phi's. And then you get an effective action written only in terms of the lambda, which is the new field that you introduced. That's in the books. Okay. You do it, and you pay attention to the fact that all these fields actually can have a VEG. So it's slightly more complicated than the typical case where the VEG is 0. But that's okay. You know what to do. The important is the integral over the phi's can be computed. It's just Gaussian. What you get is an effective action for lambda, a leading order in n, lambda is constant. So your equation for the sample of this path integral is just minimizing whatever you got at the end. A little bit more technical, you can, for example, regularize the determinant that you get from the bosons in terms of zeta functions. And then you massage the thing a little bit. And what you find is that the free energy, which is the thing we're interested in, minus the log of the partition function, is given by a zeta function, which depends on this parameter mu, plus this thing here, where the charge appears. And this parameter mu is obtained by solving this other equation here. and you stare at it, and you realize that this is the derivative of that. You stare at it hard enough, and you realize that what you've written is a Legendre transform. And it had to be so. Because you have free energy, fixed charge, you have a ground potential, fixed chemical potential. In the large N, which is the thermodynamical limit, they have to be related by Legendre transform. The Legendre transform is just taking the Fourier transform we had before, writing a saddle point approximation for that one, equal the sum. That's it. The point is that in this case, my ground potential here is a function that I know, just a zeta function. It's a zeta function on the sphere. It might be complicated, but I know it. So I can just put it in and compute. In particular, for this zeta function, we use some, okay, we see it in a second, but the important news is that you can actually solve all the problems. And what do you find at the end of the day? You find that your free energy is given by something times charge to the 3/2 plus curvature, something charge to the 1/2. But here, we're not in the O2 model where we do nothing. Here we have computed this thing. So these coefficients C3/2, C1/2 that before were just unknown to us, they can be computed. They're written there. Okay? So a little bit more in detail, what you find is that you have an expansion that looks like that, and why stop here? You can go on. Right? So it starts at q to 3/2, then it's q to 1/2. The coefficients, as I said, you can compute. But now there's something interesting that I have no idea before. I can compute every single term of this expansion, but turns out there's a surprise, or maybe not a surprise if you know quantum field theory. At some point, the coefficient of these terms start to become, instead of smaller and smaller, at some point, whoop, they go up. This expansion is an asymptotic expansion. It's not true that if I have 200 million terms, I get a better result in general. At some point, I get an error. And I can estimate the error. And in this case, I can tell you precisely that this error has to go like the exponential of minus the square root of the charge. That, by the way, is surprising in itself. It's not how a well-behaved QFT should behave. In a well-behaved QFT, if the controlling parameter is 1 over lambda, the correction should be given by e to the minus lambda, not square root. Okay, so that's something to learn. Nonetheless, by the way, yes.
Well, maybe you're going to answer. I was going to ask the q to the 0 term.
Yes, thank you. That's it. Okay, so I will not do the calculation, but at least I want to tell you how we do the calculation. Remember, to compute the effective action, we integrated out all the bosons. And we just got lambda, and then we get an effective action to lambda. But that's really like taking your fruit and throwing it in a mixer. Okay? Let's keep one out. So I integrate out n minus 1 bosons, and I keep one out. And then I get an effective action for that one. That effective action will give me the first 1 over n correction to the leading order result. Now, I claimed the q to the 0 term that Miguel is asking about is universal. If it is universal, in particular, it cannot depend on n. The leading order in n itself is linear in n. So it cannot come from the leading order. It has to come exactly from the first correction, because you have everything going like n, first correction 1 over n, n to the 0. This has a hope of being universal. And it is. You actually do the computation and you find exactly that. But it's such much a pain in the ass that you have to be happy with this. Very good. So was it worth doing all this game? Okay. I claim that yes. If anything, because we get this number from large n. So now we believe it. Here it's much more complicated, but it comes out the same number because at the end it's the same data function. But now we know these numbers here, the C3/2, C1/2. So we can ask, is that true? The only way to answer this question is lattice. I showed you the result O2. then I have to convince 3 of my friends, but then they need all 4, then they need all 6, then they need all 8. These are things that are super complicated on practice. So this is really 2 years of work. But at the end of the day, you find the following. All the ON models work exactly as you would expect. You can compute these coefficients just by fitting n equals 2, n equals 4, n equals 6, and that's what you get. So the dots are the experimental points. The line is the leading end. So this is not supposed to work, right? At least not when n is more. And same for the other coefficients. Now, it's good. What I mean to say is that this is just the leading end approximation of these terms. What I can claim, and it's true, is that this kind of expansion here does work in every end. And the coefficients that you get are at least consistent with the prediction of that end. That's, of course, much more complicated than than this one, because that's the leading effect, that's the leading already. But, I mean, it's good to me.
So for each of these points, you have a curve like that.
That's correct. So for each of these points, well, for each of these pair of points, really, I have a curve vector at the beginning, I get the 2 numbers, I put them in, and repeat for as much as they could do, and that's okay. So I said asymptotic expansion, right?
Is there what you definitely just the standard large N expansion that you
And not really. I'm testing the fact that, so here's the thing.
you just computed the result for any charge, and then at the end you expanded it.
That's correct, that's correct, that's correct.
So you're just testing whether large N expansion makes sense.
No, that
For this plot, I mean.
no, I completely agree. The question, though, is that it wasn't obvious to me at all from the beginning that if you did this large N expansion, then there's an asymptotic expansion such that you do 3/2 at the end.
Sure.
That was
Yes.
the non-obvious.
Yeah.
And then I completely agree. This is just a check that I did the calculations right. I completely agree. But it turns out that, you see, I don't really have control when N is 4. So how do I know that this actually applies? You would expect, you would hope for it if you want. You see what I'm trying to say? I cannot do the calculation for all 4. I can do it for all 2 medium. But it still works. That's maybe the mistake. But I agree, and of course I agree. Now, I said asymptotic expansions, and I also said this thing, all the terms are going up. Can we learn a little bit more from that? And can we learn things from large N that then we can use for finite N, where we don't know anything? The claim is that yes. And as I said, it all starts with observing that this equation that I've written here for writing the free energy at the saddle in the generic surface has the form of a Legendre transform. So in fact, you can think of it like more like this. No, it's Legendre transform of some function, and this function is a zeta function. Now, it's a zeta function, then you can represent it, for example, in the many representations. So just the zeta function is nothing else than the integral of the trace of the heat kernel. And now, you see, we want large charge. Large charge is large mu. If mu is large, in this integral, t has to be small. That's where the integral is concentrated. So the problem of large charge becomes the problem of small time for the heat kernel. But that's great news, because if you want to solve the problem of small time for the heat kernel, you just need to go and look at Wikipedia, because that's a classical problem. It's the Seeley-DeWitt problem, if you want. So the question is, I have the Laplacian on a generic surface, because I want it on the sphere, might as well do for any surface. And then can I compute the small t approximation of this trace of the heat kernel? The answer is yes. This expansion depends only on the geometry. So it's tensor volume, the curvature, and all the other invariant tensors. And you see, the large charge expansion is actually just this. The terms that I get, the Q3 Q1 Q1 blah, 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 these are nothing else than the leading term here in this Seeley-DeWitt expansion, and then the second, the third, and the fourth, and so on. In fact, for example, the second term contains the curvature. Remember, the Q2 1/2 term contains the curvature. They cast directly. One term here is one term there. Now, the cool thing is that I can just forget about this expansion and just look at the data function, this heat trace directly. Because if I do that, I can start seeing exponential corrections. In particular, if let's do it on the torus a moment, okay? Just because the math is much easier. Well, the modes of the torus are just modes of the torus. The heat kernel on the torus is a theta function. No big surprise. It had to be modular invariant. And that you just want this theta function here for small t, because small t is not charged. This way of looking at this mode of this modular function is not good if you want the limit of small t. You do a Poisson transformation, Poisson resummation. Well, you get this expression here. Now, this is exact in large limit. It's not just an expansion, q to the 3 to the 1 half. No, this contains absolutely every possible term. It's it. Okay, so you can write. Yes. Oh God, really? Good. Okay, I get the end resurgence. I say nothing about the flow. So ask me questions later. Okay, so what happens is that now I can write my ground potential and from that the free energy, but not just the leading term that gives you 3 halves for it. I can write everything. All the exponential corrections are written. And so generically, what do I find? Well, what I find is that there is a 1 over q expansion, but for the torus, there is literally one term in the expansion. And then there are exponential corrections that, you see, start going like a square root of q. That's what I said before. Now, this is the torus, which is very easy. The sphere is more complicated. Why is it more complicated? It's more complicated because when you try to write the heat kernel expansion, even before you get to any exponentials, you don't get one term, like in the torus, but you get infinite terms, and these infinite terms diverge. Actually, the really David coefficients diverge like n factorial. Okay, so you already have an infinite sum before you start. Good, so what do you do? Well, what you do is that you say, oh, but that's not just a sum, it's a transeries. The fact that this diverges exponentially means that secretly in the system there were exponential corrections. Okay. And you know that they are related, the perturbative part and the non-perturbative part are related by consistency conditions. So concretely, what do you do? Well, concretely, you do Borel summation, right? So in the Borel summation, you take your diverging sum, you divide it by something, gamma factorials essentially, you sum this thing here, and then you do a Laplace transform that should give you back here, right? That's the logic. Of course, this breaks at some point here. Where does it break? Is that when I do this Laplace transform, I'm integrating between 0 and infinity, some expression that might have poles. It has poles. The fact that there are poles means that when I try to integrate like this, I have to go either up or down. So my series starts getting imaginary terms, because in the integration I have to go up. So I get a bunch of residues corresponding to these poles here, and each of those is an exponential correction. And that's the effect of non-perturbative correction. That's where the exponentials come. This is complicated to look at because from here you don't know anymore what to do. You have a series, it is divergent, then you try to resum it, get a bunch of poles, and you need a prescription. Do I go up? Do I go down? Do I take the average? Do I take the difference? What do I do? So you need to think, and you really need more ingredients here. The cool thing is that you're writing a heat kernel for a Laplacian. And the heat kernel for a Laplacian, you can understand as the path integral for a quantum particle. It's the same thing. So what does it mean? Well, it means that your heat kernel has is a path integral, is a sum over saddles with expansions around each saddle. But these are the saddles for a free particle moving on a surface, and each saddle corresponds to, well, a geodesic, because these are the minimal solutions for the particle moving on the surface. So it means that generically, your heat kernel will be the sum of fluctuations, and then for each geodesic, there's going to be an exponential term with fluctuations around. Let's do it for the torus. In the torus, the geodesics are just lines that go around. Well, you can understand in terms of the lattice, but you can define the geodesics like that, and they form a lattice themselves. The torus is just quadratic, so the fluctuations decouple, so they are the same for everything. So the fluctuations around each of the geodesics have to be the same. So the total path integral is the sum over all the geodesics, all multiplied by the same term. Very good. You do that, and you get exactly the form that you had gotten before from the Poisson expansion, from the Poisson resumation. It's literally the same thing. But now you understand it as sum over geodesics on the torus. On the sphere, there's a complication because geodesics are, well, maximal circles. So they're not just fluctuations like on the torus, but you can take a geodesic and rotate it like that and see the geodesic. There's zero mode. But it's worse than that because you cannot close a sphere. So you take your geodesics and this thing will collapse. These are unstable. Nonetheless, you must sum over all of them. But what happens when you sum over these ones? Well, they're unstable. You get imaginary terms. These are exactly the imaginary terms that you got before from going around the residues. You do the calculation, and magically everything, well, not magically, as it should, the poles that you get from one expansion get cancelled with the contributions of the poles that you get from this restriction. And at the end of the day, you can compute something, which is the grand potential, which is real, which contains both the asymptotic expansion and all the exponential corrections. Let me just say one thing, and I close with that. This was in large N. So do we learn anything at all for small n from all of this? Well, we learn, if we assume that it's a geometrical picture where the non-perturbative corrections to everything come from the same origin. These are literally particles going around the sphere, these geodesics. And these are massive particles. And this system is literally one mass, which is chemical potential, because this system is, again, a formative theory. There's only one scale, which is one I put in. So if this is the good picture at any end, it means automatically that A, the expansion in Q, then we'll have asymptotic, we'll have corrections, which go like square root of Q, because they go like mu, and mu is square root of Q. Moreover, you can estimate how many terms you need, because you can do a truncation, an optimal truncation, just by knowing that. And you can ask, how many terms do I need to actually get the optimal truncation in general? You do that, what you find is that the optimal truncation happens after square root Q terms, with an error that goes like e to the minus square root of Q. Just by assuming that this is the right picture. That's all you need. Q goes up to 10. You need roughly 3 terms. That's as many as we can. With Q going around like 10, the error that you should get from this formula here is 10 to the minus 1. You look at what happens on the lattice, the error there is 10 to the minus 1. So, resurgence, at least the picture that you get from resurgence at large N, you can only do resurgence at large N, of course, but the picture of how things work remains. And that seems to give you enough information to understand why this thing works down here, because I kept really an optimal truncation of my theory. And even the order of magnitude of the errors that you get both here and here seem to be working fine. Okay, I think I close here because I'm going to be already out of time. And okay, if you're interested in what happens away from the conformal point, just ask me. Thank you.
The question?
Yeah.
Yeah, go ahead.
So this no further behavior, e to minus square root of q. It's similar to what happens in string sharing or large expansion of the matrix model. Does it suggest that there should be some matrix model like alternative description?
I
More
think so.
generally?
I honestly think so, because the fact that you have square roots means that you're diverging like 12 factorial.
Right.
Exactly like an theory, exactly like a string. So the idea is that maybe one can define something like Zohar did for the supersymmetric system. So you could think that you could give an alternative description in terms of matrices, where there is the size of the matrices that change, and that would be a natural way of expecting the square root of Q. In practice, before Zohar did the supersymmetric case, we have been trying to do something like that, failing miserably for years. And if you don't, this is not supersymmetric. So I don't know. I mean, I wish I could do it, and it suggests I totally agree.
More questions?
If I have a question which is very speculative, this machinery that you developed for this large Q collaboration theory, let's put it this way. Can this be used in John-Simon's matter theories?
Yes. So, okay, this is one of the things I didn't talk well. There's a lot of things that have been done. There is actually a very nice construction there, especially for the supersymmetric theory. Why? Because everything I said here doesn't really apply to the supersymmetric theory, in the sense that you can still write an effective action, but it will look different. In particular, there's not going to be this cumulative halves, depending on if fixing the charge you break all supersymmetry or preserve half of it, and then BPS or not. It turns out that you can. There is some work by Massless and Collaborators where they looked at Chern-Simons matter. And they try to understand how much of this applies and in which limit you reproduce the supersymmetric behavior and which you reproduce the non-supersymmetric behavior. So some work exists. There's also some work on what happens if I try to do this without parity. That it should be at least philosophically close to that. So yes, people are doing that.
I was wondering that there are many kinds of dualities and conjectures, like level rank dualities, and polymerization dualities. This could be a ground where you can check.
Absolutely. Absolutely. So I'd say in case when you know what the dualities are, you should at least check that they work. More philosophically, I think this could be useful, should be useful for dualities, because since here you have well, philosophically, as it's not, you have control over a strongly coupled system. So maybe you manage to classicalize all dualities, even if they're strong, weak dualities. But to be fully honest, there's not much work done on it. That's something that I would love to explore, but it's not there.
Is there some analog of this story for spin instead of charge?
Yes, the spin question. I get asked this a lot, and I wish I could answer the question properly. It looks like the large spin limit works differently. At some point, I don't know if it's a good picture, but I guess that there's the difference if the lowest state can be thought as a condensation of a lot of quanta, which is like here, or more like one single quantum state that has all the charge, all the spin in itself. That looks different. Now, people have been looking into intermediate regimes. So like study this, add the spin, add the charge, and see how far can you get and what kind of simplification you can get. So some regimes are well understood. Unfortunately, the regime that you'll be interested in, which is the one where there's large spin, and when spin is very large with respect to the charge, and you would like to understand to make connections with all the work of large spin, seems to be complicated. I mean, it gets more and more complicated, just technically. That's what I would say. I think Shorter published something at some point when we're on, when it's remembered. About spinning. I don't know, maybe I misremember. I'm sorry, I misremember. I know that Zohar is doing stuff related to that. I've seen some preliminary results, but I don't.
So we already have a pretty good understanding of the physics of large spin.
I know, but the question is, the complicated thing here is getting some intermediate regime where you can use both large speed and large charge and then show that you get something consistent. That seems complicated. That's what I'm trying to say. And it looks like even though philosophically it's similar, it looks like then in practice, when you actually write the actions, when you try to write it as a semi-classical description, it looks different. But I don't know. I mean, I wish I knew that.
Yes, it depends very crucially on the kind of theory that you're considering. Because say that you like the easy model, we know that the lowest energy state with high spin, we know how to describe it in terms of a single rate trajectory.
Right.
But in more complicated CFTs, this might not be the case. Maybe there will be many states.
So there was the work of Giboidov and Jafferis where they try to think in these terms, but it is complicated. So that's the short answer. It's complicated. They got out some of the results that are shown. They got out just thinking like that, but only some of them. It seems complicated. That's the way. It doesn't seem that it's really giving you an advantage in computation.
More questions?